Good morning, everybody. Welcome back to the latest Collision Hub webinar from Miller Electric again. I've got Ace back with us today. We're going to talk about steel welding basics, some best practices today. So a lot of great information in our last webinar, which is available on the replay channel if you're interested in seeing that. Just talking about basic setup, polarity, contact tip, shielding gas, a lot of things that I think a lot of us as experienced welders we tend to forget over time. So it was a great refresher, as well as a great course for many of those that aren't as familiar with welding and how to set machines up. So really appreciate that. And we'll have one more Miller Electric presentation a week from today, talking about aluminum welding. So I'm not going to spend much more time. I want to get right into it this morning. Again, we're on the webinar feature today, not the meeting feature, so you can't talk unless you raise your hand, and we promote you to do that. But use the Q&A at the bottom or the chat feature at the bottom. If you've got any questions throughout the presentation, please feel free to chime in and let us know, and we'll share that. We'll try to answer those questions as Ace goes through this. So. With that, Ace, I'm going to turn over to you, and you can go ahead and kick it off. Appreciate it. Ace, I think we lost your audio there. I'm not sure if you're there.
Can you hear me now?
Now we're good.
Yeah, here we go.
Perfect. So, like Jason was saying, today we're going to be talking about welding of steel and dissimilar metals. Pretty excited to talk about this topic because it's pretty hot in the industry right now, especially in the auto collision industry. So first off today, I want to talk about some types of steel that are used in auto collision repair. I want to talk about how do we weld them, what is silicon bronze versus mild steel setup. I'm going to jump into some metal transfers and then move into process parameter adjustments, talk about some joint types and techniques. All right, let's get started. So types of steel. So nowadays, cars are starting to get lighter, trying to improve fuel economy. So one way to do that is to make cars out of thinner material, but look at different ways of strengthening that material. Like I said in the last presentation, I'm working on a old 74 Ford Bronco, and that thing is like a tank, all made of steel, and there's no mixture of really anything in that. But nowadays you might see cars with some mild steel, you'll see cars with high strength steel, and one other that I was going to call out is galvanneal, and that's a steel that's been galvanized and then annealed. Creates a hard coating on the outside that helps strengthen it and protect it from corrosion. On the next couple slides here, I'm going to pass the mic over to Joe and let him talk for a minute.
Thanks, Ace. Yeah, to Ace's point, we all know that the structure is changing dramatically in all the vehicles coming off the assembly line these days. The diagram on the left is the B pillar to the new Ford Focus over here. And if you look at that, it's not just punched out cold rolled steel or anything like that. Ford, in their infinite wisdom, is using a lot of this boron because of its structural integrity and crash resistance in here. So you can't exactly weld boron the same as you would regular stamped steel. So if you look at those, that B pillar, you've got a few different types of metal in there. You got some conventional steel, you got a little bit of the galvanized, and you've got some boron in there, again, to maintain some structural integrity. One of the best diagrams, I use this picture a lot. It's probably not the best one that I have, but the picture on the right is an Acura RDX. Honda had it at the trade show in New Jersey a year or so ago, and another iCar conference, and had an opportunity to speak to the woman who headed the design team on this vehicle. And according to American Honda, this Acura RDX is probably one of the safest cars that you could be in should you have the unfortunate situation being broadsided because of the different types of materials. The red that you see on the side is, they call them like a unicide, which you guys mostly know about. and that is actually boron steel. They assemble it in some sections, do some laser welding, and then they squeeze type resistance it and use different adhesives to bond it to the rest of the vehicle. The aluminum you can see down inside that, the yellow piece down inside the rocker panel inside the door aperture is actually a forged aluminum structure that's panel bonded to the inner rocker panel and then enclosed over it. So by using that, it creates an extremely lightweight but incredibly strong structure. So hence the case, if you happen to be unfortunate to be broadside in one of these things, the structural integrity of the car is going to remain intact and again provide for passenger safety. And then in the back you see some of the blue. That's more of your conventional lighter high strength steels that they're using structurally on the vehicle and so forth. So on every vehicle, this is why it's so important to follow OEM recommendations and do your research so that you find out exactly what you're dealing with. Just going to grab a MIG weld and start welding away on this stuff anymore. You just can't do it. It's just you just don't know what you're working with anymore. So, and this is just a couple of more slides that. If you look at the top left, both General Motors vehicles, you look at a late model Chevy Malibu, the light fluorescent green is actually aluminum. So if you look at the Malibu compared to the Cadillac CT6, there's a vast difference in the amount of aluminum being used in that. But if you look at the some of the structure on the vehicle, B-pillar, windshield posts up into the roof. Again, that's what they're using all these ultra high strength materials, and they certainly require different welding techniques. Down the bottom again is just one from Chrysler Dodge with the just on the side of that particular vehicle that you've got 4 different types of material all in the same area. So if some you got hit in the doorpost or right broadsided, you've got 3 or 4 different metals that you need to deal with, and this is why we've advanced to what we have with the silicon bronze and squeeze type resistant spot welders and the adhesives today. It's just not the same as it used to be. So there you go.
Perfect. Thanks, Joe.
You're welcome.
So what I'd like to shift to is, so we have all these different types of metals that are going into cars, but how do we weld them? So first, steel will typically use GMAW short circuit, which we covered quite a bit in the last webinar. A new one that I'd like to talk about is joining dissimilar metals. A very common process or filler metal to use is silicon bronze with either the short circuit process or pulse spray transfer. So what is silicon bronze? So it's a type of filler metal. It derives from back in the day when they'd use an oxyacetylene torch and they would use a brazing rod. Well, this process now allows you to have that wire come through a MIG gun and use a constant voltage machine to weld your pieces together or MIG braze them together. So one of the really cool things about silicon bronze is you can join all different types of material. It's really commonly used a lot in high strength steel and also in galvanneal. So some common diameters for silicon bronze, it typically you'll see 025, 030, 035, 040. One thing I wanted to also talk about was that different car manufacturers do require they might have a specific silicon bronze wire that they want you to run when you're repairing that vehicle. So keep that in mind when you are working on repairing cars. So let's talk about some differences between silicon bronze and mild steel. Silicon bronze melts at a much lower temperature than the base metal you're welding on, and also it melts at a lot lower temperature than solid steel wire. The tensile strength is also a bit less than steel, as I have there about 50,000 psi versus 70,000 psi. One of the really cool things about silicon bronze is the capillary action that occurs when you're using it. So what the capillary action is in the pictures over on the right, I just did a quick weld this morning on some steel plate that I had, or some sheet metal. And so this is the top side of the weld. And what that capillary action is, it's when that filler metal gets drawn through to the backside, and you can see that additional buildup on the backside in the picture on the right. And what's really nice about that is that helps to keep the structural integrity there. So when you go to do the repair work and you grind off the weld so it's nice and smooth so you can do whatever auto body work you need to do to it, you still have all that strength on the backside and in the joint. So some of the benefits of silicon bronze is, first, it'll help reduce distortion because there's less heat input. You can join different materials together, different types of steel. It's really good with thin material because of its low heat input. And because of that, you can do all different types of joints, but it works really well in open root joint types. So next I wanted to kind of talk about, the last webinar we talked a lot about getting your machine set up for welding with steel. And today I just kind of wanted to compare a little bit between setting your machine up with silicon bronze versus setting it up with steel. So over on the left, the common shielding gas that's used with silicon bronze is 100% argon. Typical flow rate will be between 25 and 35 cubic feet per hour. The wire type is an ERCUSI-A, and that might vary dependent on the manufacturer. Some good drive rolls to use would be either U-groove or V-groove. The polarity, direct current electropositive, and a good liner to use is Teflon. One note also there is the silicon bronze wire is softer than a regular solid steel wire. And one thing you might want to keep in mind when you are using that is typically use like a shorter gun, like a 10-foot gun, to eliminate any bird nesting issues. So as opposed to a steel setup, if you're welding on mild steel, you'd typically be using a 75% argon, 25% CO2, or 100% CO2 shielding gas. Flow rate of 25 to 35 CFH. Typical steel wire is going to be ER70S6. Lining that up with a V-groove drive roll, polarity, direct current electropositive, and typically the kind of liner that you use is steel coil liner. One thing I might reiterate from what I had talked about previously is always ensure that you have your wire diameter matched up with your drive roll diameter and also with your contact tip diameter. It's really important that you always keep those consistent. Moving on, so I wanted to touch base on metal transfers. So we're going to get a little bit more in depth with these, but the three I really want to talk about today is going to be short circuit transfer, pulse spray transfer, and spray transfer. And pulse spray transfer is a derivative of spray transfer. So in this diagram here, looking from left to right, we have voltage over on the left and amperage across the bottom. Now, if we were talking in terms of heat input, short circuit transfer is going to be the coldest metal transfer that is capable right now for this chart. If we're looking at the different modes, globular transfer is going to be maybe a little bit hotter than a pulse spray transfer, but a spray transfer will definitely be the hottest. Now, I just want to touch base. We're going to watch a couple of videos in a second because I really want to talk about what's happening at the end of the wire and just give you just a little example so that when you do go out to weld, you can kind of see what's going on there. So what's going to happen in this first video, we're going to be talking about short circuit. And what you'll see is the wire is going to come down, make contact. The amperage is going to increase and clear the short because that wire's made contact. And then what you're going to see is the arc will stay on. Slight ball will grow. It's going to touch again, and you'll see that transfer. So there it is at a high speed. Now it's at a low speed. So you see that contact made, clears. There's a little bit of an arc there, ball building. It's going to make contact again. And that can happen anywhere from 90 to 200 times per second. A typical voltage range you'll see is from 10 to 21 volts for short circuit transfer. So spray transfer is going to differ because as you start increasing your voltage from short circuit, you're going to start changing your transfer mode. And once you get into a high voltage, you're going to be towards a spray transfer. So I just wanted to pull up this diagram here. I really like it because it shows kind of what's going on, and we can talk through that. So we have our nozzle here, contact tip inside, wire coming out of the contact tip or our electrode. And so we have our arc. We have our shielding gas that's protecting our arc and our molten puddle from any oxygen or anything that might contaminate the puddle. And then as you'll see, there's a pretty good distance between the end of the wire and the puddle itself. And what's happening is little droplets of metal are being pinched off and thrown across that arc into that molten puddle. And typically there's hundreds per second. So I got a video here. Let's watch and we'll see the difference.
In spray arc transfer.
I apologize.
In spray arc transfer, a continuous stream of tiny molten drops, usually smaller than the diameter of the wire, are sprayed across the arc from the electrode placement. With spray arc transfer, the arc is on all the time.
One of the things that you'll notice is, so there is that good distance in between the end of the wire and the puddle. We have our arc here, and it definitely sounds different than short circuit. You don't get that buzz, you have more of a hiss sound. So spray transfer isn't typically used in auto collision, but I kind of want to talk about it a little bit because so spray transfer is used in industry a lot, but it's usually used towards thicker plate, like 1/8 inch or thicker. Good thing about it is you get high deposition rates, so you transfer a lot of metal quickly. It allows you to travel fast, and because you're never shorting, there's little to no spatter. You can also run large diameter wires. Some of the limitations, like I had said, it's limited to 1/8 inch and thicker. Works best in flat and horizontal position. Typically, you don't see it used out of position. And typically, you get really good penetration from it. So pulse spray transfer, now we're going to take, and instead of just doing a constant stream of droplets across that arc, you're going to see that in slow motion, you'll see that as the current rises, once we hit this peak, that'll allow us to transfer a droplet, and then we'll move to our background amperage, and that'll keep our arc maintained. So basically, we're going in between a high current and a low current or amperage, and that helps us to take that weld out of position if we need to. So we could go vertical, we could go overhead, we could do horizontal, flat, whichever way we need to. But one of the really nice parts about that as well is you can eliminate a lot of spatter and get a really nice arc. So let's go ahead, let's watch this video, and it's going to show, you can hear right off the bat that the sound is different. You have a little bit of a buzz, but so as you're looking at that arc, we have our arc here. It's transferring one droplet with each pulse there. And so we can really control how much metal we want deposited. So pulse is getting really popular. Like I had said, when we're going, if we're looking at a waveform of what's happening with the voltage and the amperage, as your amperage goes to the peak, it's going to be transferring a droplet, which helps push it across the arc. And then as you go to your background, it helps maintain that arc, keeps it lit. So one of the things I want to talk about next was, how do our parameters differ between short circuit and spray transfer versus pulse? What would we adjust on each machine? And then we're going to look at I took some welds with silicon bronze, took some pictures of them, and we're just going to talk through those and how that affected that weld puddle. So typically with short circuit or spray transfer, you're going to be using voltage and wire feed speed to adjust your parameters on your machine. Those are going to need to be dialed in accordingly. If you're running pulse spray transfer, pulse is synergic. So you have a couple of adjustments. You're going to have a wire feed speed adjustment and also an arc length or trim or arc adjust. It's a lot of the terms are adjusting the same thing, but what that's going to do is it's going to allow you to adjust the distance in between the end of your wire and your weld puddle. So as you decrease that arc length, it'll tighten that up, or if you increase it, it'll make it longer. What's going to happen is it might affect your puddle width a little bit. If you need to narrow up the puddle, you can always tighten it up a bit. It also helps dependent on the joint type that you're going to be welding up. So it allows you to adjust that. As your wire feed speed increases, your heat input increases. So it's synergic. So once you set your arc length, that distance between the end of your wire and the puddle, the machine is going to be synergic with your wire feed speed. So as you adjust your wire feed speed, it's going to maintain that same distance, no matter where the wire feed speed is. But as you increase your wire feed speed, your metal deposition will also increase. So let's dive in a little bit more into the short circuit adjustments. So voltage will control the width and the shape of the weld bead. It'll also control the arc length. So as we were talking about before, once we start getting into a high voltage, that'll change our transfer, changes our arc length. Typically what you'll see with silicon bronze though is a really low voltage is used versus like a solid steel wire. For wire feed speed, it'll adjust the amount of material being deposited, and it'll also affect your penetration. So I got a couple pictures here, and basically as we're looking across there, so all I did with these three welds is I adjusted my voltage slightly. So the first weld here, I just called a nominal setting. Just dialed in the arc, had it nice and smooth, and then what I did was moving over to this weld, I dropped my voltage about 2 volts, and what you can see is it got a little more ropey, a little more buildup, didn't quite wash out as much on the toes. And then on this third weld, what I did was I really increased the voltage, and you can see that puddle just washed out a lot. It also had an effect on how much steel it drew into that weld puddle. And then looking at the bottom, this is the back side of that. So pretty normal amount of heat input. The first two were pretty close, and then you can see at that third one with all that extra voltage, it really affected that heat affected zone. You can see how much dark gray there is out here. So you want to make sure that you dial in those parameters for the joint and specifically for the car you're going to be working on. So pulse adjustments. Like I had said before, arc length or trim or arc adjust, that's going to change the distance in between the end of the wire and the puddle. Typically what I recommend is start out with the nominal setting for that when you are dialing in for silicon bronze, and then adjust for what you need necessary, because for each joint type, you might have to adjust that a little bit depending on what you like. As far as wire feed speed goes, it'll adjust your heat input, your droplets transferred per second, or pulses transferred, or pulses per second. And typically you'll see running pulse on sheet metal with silicon bronze, it'll be on the low end of the machine, so low wire feed speed to limit that heat input. So here's a couple welds I took. So basically I just dialed in the arc using pulse. This was my nominal wire feed speed at 190 inches per minute here. It was just a parameter I dialed in and just did a weld with, and then I wanted to see show what the difference was if I really increased that wire feed speed or if I dropped it down. And so as you see, as I took that up to 300, it really added a lot more heat into that. You can see that it drew more steel into the weld puddle. And then as I really dropped that down, I really took a lot of heat out of the arc, and you can see that it got really ropey on top of that plate and didn't wash out at the toes like we would want it to. So I'd like to transition a little bit and talk a little bit more about technique when we're welding with silicon bronze and short circuit transfer. We talked a little bit about it in the last webinar, but I'd like to just reiterate some of the things that you might see there. So first off, I want to talk about travel speed. So in the weld down below, it's really important that you maintain a consistent travel speed when you are welding with whether it's steel or silicon bronze. Technique usually is the same. So it'll affect your heat input into the plate. So looking at these three welds, you can see a size difference between them. So here I was using a rather slow travel speed. The middle weld, I had picked up the pace a little bit as I was moving down. And then the third weld, I was really traveling fast as I was going across there. So just a couple of things to keep in mind. It'll affect the heat going into the plate. The slower you're traveling, the more heat you'll get. The faster you travel, the less heat you'll get into the plate, and then it also affects that weld size. So travel angle. Typically what I'll see a lot is using a push technique when you're using silicon bronze, especially when you're welding with pulse, you want to be on the leading edge of that puddle. So typically if you're moving from left to right, you'd want to be using this push angle. Next one I want to talk about was work angle or torch angle. And the thing to keep in mind is where you point the wire, the weld will follow. So as you can see in the fillet weld that we have here, brought in at a 45, it'll wash that weld puddle up onto the top plate and the bottom plate 50-50, which is what you want. Now when we're doing a butt joint like this one, want to come in so you're perpendicular to the plate, and then it'll wash onto both pieces. If you were more positive or negative, you'd see that weld build up on one side or the other. The main issue there is if you don't have the correct work or torch angle, you might not see as much reinforcement or penetration that you would need. So a couple positions that are pretty common with auto collision are going to be flat position, which is typically easiest to weld. I actually don't have a picture of it in here right now, but here this will be horizontal position. This will also be horizontal position. This one looks a little bit goofy, but since it's a lap joint and we are welding it in that direction, it would be a horizontal. And then vertical would be moving straight up, and then overhead, which nowadays it's pretty difficult. Usually welders, when they are welding, they'll try to weld everything they can in flat position because it's usually the easiest one to weld in. However, if you're rebuilding a car, working on a car, you don't have that luxury of being able to flip the car over and keep all the welds in the flat position. So as you are in different positions, you may need to adjust your weld settings accordingly. So all machines might not have the same parameter. They might not have parameters for silicon bronze. One thing that you might end up having to do is dial in those parameters yourself and do a weld test to verify them. So maybe Jason, I'd just like to thank everyone for the opportunity to get to talk to you guys about silicon bronze and welding on steel and dissimilar metals today. Maybe we'll just recap with some questions real quick. Jason, can I have you come back on?
Yeah,
Excellent.
I am here. We don't have any questions coming in. Oh, hang on, we do have one. We just got one here. Oh, cool.
Perfect.
Thanks, man. Just a thank you from Brian. Thank you for that, Brian. So, a couple of things I wanted to mention. If you can go, would you mind going back to that? It was really early, and I didn't want to interrupt you, but the picture with the Ford Fusion and the RDX
Oh, yeah.
there,
Yep.
Absolutely.
way at the beginning.
Next one.
Yeah,
you go.
there. So one thing, when it comes to Honda and Acura vehicles, if you're repairing a late model Honda and Acura vehicle, you know, whether that's an RDX here, an MDX, an Accord, an Odyssey, a Civic, any of them, anything starting probably 2015, 16, when they started making the switch to that 1500 MPa steel, in the side aperture, A-pillar reinforcements, B-pillar rocker panel, even the rear rails on the Civic. If you're repairing Honda vehicles, you have to have MIG brazing equipment, and you have to know how to use that MIG brazing equipment. There are locations, so spot welding is a preferred method for attachment on all those panels. However, there are several locations, most notably at the base of the B-pillar near the rocker panel area, where you cannot access those joints with a spot weld. You don't have access to that backside, and in those locations, Honda calls for MIG brazing. And they're called for MIG brazing using pulse spray transfer, as Ace went through, not short circuit. Volkswagen allows either or, but Honda is all spray transfer requirement for all their vehicles. But you have to use silicon bronze in those areas to repair the vehicle properly. And additionally, one thing when it comes to Honda is, a lot of the OEMs you'll see when they call for MIG brazing, they'll use a slot weld, like an elongated oval hole, usually close to an inch long. On Honda vehicles, they recommend using side-by-side, essentially plug weld holes, and a zigzag pattern. And Honda's got a lot of great information on their website for this. So if you go to the Service Express website, in their body repair news area, you can access those for free. You don't have to buy a subscription. You can access all those body news articles for all their vehicles that they've been releasing on each new model, which is fantastic. But it's quite unique and a little bit different for us. Again, making that kind of zigzag pattern on these dual plug welds, plug weld hole looking things, I should say, for it. So it's quite unique in that sense. And one question that I get quite often, and maybe Ace and Joe could back me up on this a little bit, but because we're using lower heat, we're not making a fusion weld, so we're making a silicon bronze joint on these. The reason we're using that dual plug weld, or the reason we're using a slot weld, or you've seen a lot of times in seams, is because of that capillary action. That's giving us the strength in that area. So when we talk about a plug weld versus a slot weld, we're getting similar strength characteristics from a tensile strength standpoint, because we're using more surface area of that with that capillary action to kind of grab onto that metal. And that's where we get the strength on it by. And again, as a lot of us that learned how to weld and on mild steel vehicles that were thicker, we always really want to get in there and burn that metal and make sure we get a good fusion weld. And we're not trying to do that with silicon bronze. We're trying to get that capillary action, that kind of almost an adhesive property on it. So just a couple things to point out specifically around Honda Acura vehicles. But again, if you're working on Honda vehicles, you have to have MIG brazing equipment, and you have to know how to use it and use the proper electrode wire on that as well. So just wanted to point that out.
That's awesome, Jason. Maybe if I can just add one thing in there too.
Yeah.
Like, really, a question we get quite a bit too is, you know, and I was expecting to already get it, but one of the questions is, when do you use pulse? When do you use short circuit? And always my answer is refer to what the car manufacturer is telling you to do on those specific joints. So
Yep.
As always, I would always recommend that before anyone goes and repairs any vehicles, that they do it using what the car manufacturer recommends, whether it be machine and also for filler metal. So.
Yep. Thank you very much for that. So yeah, and we're seeing a lot more MIG brazing applications out there. As again, the Honda Acura stuff is well documented. GM's got some, Volkswagen, as I mentioned. So it's definitely something we need to take a look at moving forward. And one interesting thing we got that Ford Fusion picture up there from Great Designs in Steel. It's not related to welding at all, but every time I see those DP, there's a DP 1000 tube and a 1.4 and a 1.8 millimeter DP 1000 tubes in there. And I think back to a lot of people that still think we can just, with steel, I can use heat and I can straighten anything. As part of that presentation from Great Designs, and it's probably available still on the website, they showed a cutaway of the vehicle, and you can see how much additional deformation takes place in a side impact when those tubes aren't there versus when they are there. And it's almost 2 inches from my recollection, the difference between the vehicle, the baseline vehicle without the tubes and then the one with the tubes on it. And 2 inches doesn't seem like a lot, but when you're talking about a B-pillar next to the side of your head, 2 inches can be the difference between life and death. And I think that's really important for us to think about as we're repairing these vehicles, of why they're there, what the recommended procedures are, why we can't straighten it, why we have to make braze these Honda vehicles back together in a lot of cases. So it really goes to reinforce that. And maybe in another Collision Hub broadcast webinar, we can talk a little bit more about that and those tubes, and I can show you that, because it really is an impactful image when you take a look at it. It's something that I've used in a lot of different presentations throughout the years. Any other questions from anybody? Either, again, we'd love to have you via chat or via the Q&A session. Not really seeing anything coming in right now. Joe, you got anything that you want to add?
No, I just appreciate the opportunity to help bring a little more information to the table to all of those in the collision repair field. And like I said, to your point on on some of the structure on some of these vehicles, unless you've really seen it up close or pulled a few of these things apart, you don't have a great enough appreciation for it sometimes. And you look at this, it's like, all right, how much stuff did they sandwich between that inner and outer B pillar, or how much material or reinforcements are in between the inner and outer rocker panel? So to your point, it's like you really need to see what's in there and follow the OEM guidelines so that you really put that vehicle back into pre-accident condition and maintain the safety of the passengers at all times.
Great. Ace, anything else from you?
I don't think so. I'd just like to thank you, Jason. It was great to get to talk to you guys today about this. I am excited about next week. We're going to be talking a little bit more about aluminum and false aluminum welding. So
yeah, I'm looking forward to that too. That's again June 10th at 11 a.m. again. The webinar access is available on the Collision Hub website under events, under the events page again. So we're looking forward to having Ace and hopefully Joe back with us again next week. I do want to thank both you gentlemen for your time today, as well as all of our attendees. I do want one note. We had originally had an AirPro Diagnostics webinar scheduled for this afternoon at 1 p.m. We are pushing that one back until June 17th, same time, 1 p.m. Josh and Eric from AirPro Diagnostics are going to be with me in Little Rock, Arkansas. So we'll be coming live for that one with some static calibrations, and that one's going to be an interesting one. So hopefully looking forward to having you back at that one as well. But again, so thanks to Joe and certainly Ace for all of your efforts today, and look forward to seeing everybody a week from today. So thanks a lot, everybody. Have a great day.
All right. Thank you. Take care. Yep. Bye.